Hello and welcome to a video on how we do frequency analysis using Miller's theorem. So in this video we will be looking at high frequency analysis, how we design load capacitors after we've figured out what the highest frequency is of an amplifier, then how do we design a Miller capacitor, and we will be doing this for common emitters, common emitter amplifiers with and without the bypassed emitter resistor. Okay, so just a recap of what Miller is. That is when we have a capacitor that's in parallel with our amplifier like this, or in a feedback position rather, and we want to split it up into two different capacitors, input capacitor and output capacitor. Now for the BJT, this capacitor right here would be C mu, and we can get our input and output capacitor using the loaded gain of our amplifier. So for the plain common emitter of a bypassed emitter resistor, it's minus GMR load prime, where R load prime is all the loading effects. And for the one with unbypassed emitter resistor, we have to include the little bit of feedback at the bottom, or the degeneration. So how we would go about to do a DC analysis, a Miller analysis or AC analysis high frequency for the circuit is all our low frequency capacitors will become short circuits. This is how to set up a small signal model. We'll use the Q point to calculate the small signal parameters. Just like low frequency, we will switch off all voltage sources, all current sources. Current sources will become open circuits due to infinite impedance. All the circuits of today, or the two circuits of today, will have current sources in it. It's just easier rather than going the whole biasing route. Just make simple examples. And after that, we replace the transistor with a high frequency model. So that's very complicated model that we did in a different video. Then we keep all the high frequency capacitors in the model, and we will evaluate each capacitor separately while the others are open circuits, or we will only evaluate one or maybe two capacitors out of a bunch if we know that they are dominant. Okay, then we will calculate the resistance seen by each capacitor, and then calculate the higher cutoff frequency and do some design work. So we are going to do this using two examples. So first we have our common emitter amplifier here with a bypassed emitter, 1 milliampere current source, and the questions is we need to draw a small frequency model of amplifier, and we need to include a load and a Miller capacitor. So just to show you where they go in a small signal model. Then calculate all the small signal parameters, calculate the resistance seen by each capacitor, and then calculate the higher cutoff frequency. Then we are going to design load capacitors for when we want a higher frequency of 10 kilohertz, and then if we want a higher frequency of 50 kilohertz, and then lastly design a Miller capacitor when we want a higher cutoff frequency of 25 kilohertz. Okay, all our parameters for our transistor are down here. So we are using a C pi of 16 picofarads. Rx is 10 ohms. transition frequency of 300 megahertz, beta value of 200, early voltage of 100 volts. Beta is 200, sorry. Okay. So let's start with a small signal model. So this looks fairly straightforward. Here is our BJT high frequency model. And this is where we will place an external mirror capacitor if we need to. Note that it's not on this node right here because this is internal to the transistor. So it will go here on the outside. I've seen a lot of people drawing it right here. And a load capacitor will go across the load, of course. Okay, so those are just to indicate the two positions where these components will go if you include them. Okay, for 1 milliampere bias, we have 40 milliamperes per volt. Transconductance, 5 kilo ohm R pi, 100 kilo ohm output impedance, and C mu is 5.22 picofarads if we need to calculate it. Right. Our next slide here is what will happen to this model when we do Miller on our C mu. I did not include our load and Miller capacitor on this one. So C1 will be going in this position right here, also outside the transistor, not directly parallel to C pi, and C2 will go on this side right here. So equations, what is C2 seeing? Now for high frequency capacitors, we are trying to see what is in parallel with the capacitor. So starting with C2 is easy because it's R out parallel to RC parallel to R load. And that is useful because we also need that for our gain, our loaded gain. Then RC1, this capacitor, what is it seeing in parallel on this side? Is RS parallel to RB. And if we look to this side, we see RX in series with R pi. So Rx plus R pi is in parallel with Rs in parallel with Rb. Okay, so there's our Rx plus R pi. Now, for a very small value of Rx, right, R pi is much greater than Rx. This will reduce to R pi parallel to Rs parallel to Rb. And Rx is like 10 ohms in this case. Looking at our C pi, here it sees R pi in parallel here, and looking to that side, it sees Rx in series with a parallel combination of Rb and Rs. So again, if Rx is much smaller than Rs parallel to Rb, it will reduce to the same equation as that we have above. So you will find that in most cases or problems, people will see these two capacitors as if they are in parallel and work with R pi. Okay, so this equation right here, I'm just going to leave it at R pi parallel to Rs parallel to Rb, but you'll find that most people will be working with this equation right here. Right, so if we calculate our R pi and R load, we get 31 kilo ohms and 2.5 kilo ohms. From that we can determine our gain, because we already have a transconductance as minus 124 volts per volts. Then we can take our C mu of 5.22 picofarads and find our C1 and C2 value. So this is 625 picofarads and this is 5.26 picofarads. So this is very close to the 5.22 that we originally had. So again, for large gains, C2 and C mu will approximately be the same value. Right, then we can define a new capacitance, C in, and we call that C1 plus C pi. So this value right here plus the C pi that we had, which is 16 picofarads, and get 668.5 picofarads. And this will be the dominant pole in our equation right here. Okay, this is the largest capacitance and the largest, these two resistors are kind of equivalent. So basically this cap with this resistor will make the largest difference in our frequency. For the higher frequency, we are typically looking for the lowest frequency of the high frequencies. Okay, so we will typically have our dominant being the lowest frequency. Including C pi here is not making much of a difference, but it does get noticed. Okay, 6.5 and 6.8. 6.5 and 6.6. That is kind of noticeable. But if C pi was something small, like 4 picofarads, right, we could have just left this out in general. Okay, because then it would be something like 664. Since we're working from this one, you get the idea. It's if it can get neglected, you can just throw it away. But the 16 picos will get noticed in this. So then, to give you an idea, for our C2 value, if we go and calculate it, it is 9.76 megahertz, which is much greater than when we calculate our C in and R pi value of 95.23 kilohertz. Okay, so this one is the dominant one, and that will be the result that we see when we simulate this problem. This kind of frequency or capacitor will not make any difference. Now we have to design load capacitors. One for 10 kilohertz, one for 50 kilohertz. Now this is what is on this side is what's ideal for a load capacitor design, and that is the case where this new frequency that we are designing for is much smaller than FH that we calculated in the problem. Okay, so 10 kilohertz is much smaller than 95 kilohertz, almost 10 times smaller. Okay, now if we calculate the high frequency and we need to include things that is not dominant, everything gets added below the line like this. Okay, so we had C in and C pi, but now we want to add a C load capacitor, which will be in parallel with our load right here, right? C2, same position. Right, so everything just gets added below the line like this. Now, if H is much greater than the frequency we're designing for, this term will be the dominant one, right? And this is dominant. Then we can throw this term away, because FH prime will then be equivalent to these two components right here. Okay, so then we can calculate the load capacitor from this, and we get 5.1 nanofarads as a standard value. Right. The second one is to show you when something is not dominant. 50 kilohertz is about half of our higher cutoff frequency, so it is not a dominant pole at all, right? So we need to work with both of these in the equation at the same time, but we already know Cn and R pi, we already know our load, so it's not really a problem. This side is just to make the mathematics easier on us, and you'll find that in the simulation that this is kind of accurate. Okay, but in this one, if we neglect the effect of Cn and R pi, we will run into problems. So we just work with both of them, and we see that we need a load capacitor of 470 picofarads. Okay, so 5.1 nano, 470 pico. Our Miller capacitance. Now, 25 kilohertz, it's a quarter of this roughly. So again, not really dominant, so we can't neglect the effect of the Cin that we used. Now, we start off by adding a small capacitance to our Cin, right? So we are checking what capacitor do we need to add around here to give us the frequency response of 25 kilohertz. Right? So we do Cn plus Cx. Then we find that the value of Cx is 1.858 nanofarads. But this is not a Miller capacitor yet. Okay, it still needs to get moved to be in parallel. Where I drew it in the wrong place. Needs to be moved to the right position to be a Miller capacitor and something useful when we build it. Okay, and how we did Miller is we took our C mu and we multiplied it with a gain plus 1. Now we're just going to reverse this effect for ourselves. So Cx is equal to C Miller capacitor 1 plus AV, like this, because Miller is the one we want, but Miller is the one that we want in that feedback position over the amplifier. So Cx is going to be divided by 1 plus AV, and that gives us roughly 15 picofarads. Okay, so those are the three capacitors and the dominant frequency. Let's go and check out all four of these in simulation quickly and see how accurate it was. Alright, so here is our original circuit. Let's run it and take the output. Let's see, our maximum gain here seems to be 29.7, so minus 3 decibel point is 26. Okay, right here. So our higher cutoff frequency is 116 kilohertz in simulation. That is fairly close to the 95 that we got. Always remember that most of these high frequency calculations that we are doing like this is rough estimates. The only way to get a very, very accurate result is to do the direct method on an amplifier, and that is having all the capacitors and resistors in the same equation and then solving for it. And that seems like effort if you're doing a hand analysis. That is why we have simulators. In the end of the day, when you're designing, you want an estimate of what this frequency is, and to help you how to design compensation capacitors. Right, so the high frequency is fairly accurate. Let's go to our load capacitors. So our first load capacitor was 5.1 nanofarads, and that was for 10 kilohertz, right? Okay, so 29.5, 26.5 right here, and this is sitting at 9.6 kilohertz, fairly close to the 10 that we were designing for, I would say. Next up, this was 470 picofarads for our 25 kilohertz design. Okay, 29.6 or 26.6 around here, and that came out as 59 kilohertz. And remember, this was 488 picofarads, and we choose a lower value, so that's why this increased. But our result is fairly good. Next up is the Miller capacitor. Okay, our Miller was 15 picofarads. We run this. We had to design for, what was it, 25 kilohertz. Going down to 26.7. That's at 26.5 kilohertz. Right, so that is how we design load capacitors or Miller capacitors for our amplifiers. Let's go to our second common emitter problem. Right, our second problem is roughly using the same amplifier as the previous one, different input loading and biasing resistor and output load, but we also included a small emitter resistor that will not be bypassed. In this case, we are designing for 200 kilohertz for both Miller and for a load capacitor. I want to show you something else. That's why I'm choosing them the same. So let's start with our model. Same as the previous one, just this emitter resistor is included. Everything else still works out exactly the same. Now, RC2 remained the same. That is what this capacitor here is seeing. Since we typically see this as a virtual ground, other people will say if you go deeper into electronics, it is this resistor plus the gain of this amplifier multiplied by this resistor in parallel with R pi, and it's a lot of maths, and what it says in the end of the day is what is sitting here is just a big impedance, so it would actually be better just to use RC parallel with R load in those cases. But let's stick to what's known at the lower levels for now. Just note that there is more accurate and bigger equations out there. So if you run into something strange, it might be that somebody overcomplicated analysis. Right. The gain of this amplifier is including the degeneration resistor. And now for C1 and C pi, they are sitting in very different positions. Even if we neglect the effect of Rx, they are not in parallel with one another because we have Re down here. So looking at what C1 is seeing in parallel with itself, it's again Rs parallel to Rb, parallel to everything on this side. So Rx plus R pi plus beta plus 1 Re. Okay, so that is quite large. This will be a very large impedance, and Rs parallel to Rb will dominate around here. Okay, so this capacitor will heavily be affected by Rs and Rb. Okay, in R pi's case, what it's seeing in parallel directly with it is R pi. So R pi will typically be the dominant part over here, but what is R pi seeing in parallel with itself is Re beta plus 1 plus Rx plus this parallel combination over here. So we can just move this resistor up there when we still have everything this side in series. Okay, so Rs parallel to Rb plus Rx plus beta plus 1 Re. So basically Rs parallel to Rb exchanged positions with R pi for the R pi equation. Right. Now, R load prime 2.3 kilo ohms. If we calculate RC1, we get 820 ohms, and if we calculate R pi, we get 4.04 kilo ohms. Calculating the gain, we get 18.4 volts per volts. And calculating C1, we get 101.3 picofarads, and C2 is 5.5 picofarads. C1 is our dominant over here. And that gives us 1.92 megahertz cutoff. Okay. Moving on to the two designs. Our higher frequency is much greater than our new design frequency, right? This is about 2 megahertz. This is 200 kilo ohms, where is a 10 times difference, roughly. So we can work with just our load capacitor like this, and we will get that our load capacitor must be 350 picofarads. Right, for our Miller cap with C1 we add a small Cx value and we work with RC1 over here. If we calculate that, we get to 970 picofarads Taking away the 101 of C1, we get 896 picofarads. Dividing this by the gain, we got 43 picofarads as a standard value. Okay, so let's check out our simulations to see our higher frequency, if it's aligned with this 1.92 megahertz, and then our load and our Miller cap. So starting off with higher frequency, this is 23.6 decibels, so we need to go to 20.6. That is 1.9 megahertz, fairly close. Then our load capacitor of 350 picofarads. Twenty-three point 188 kilohertz. So the thing that I wanted you to notice is that this 350 picofarads is much greater than the 43 picofarads that we're going to add as a Miller cap. But let's go to that simulation. So our Miller cap is much smaller than a load capacitor. And this is an attractive solution when you can't use large capacitors. So for chip implementation. Around here, and that gives us 180 kilohertz. Okay, so both of these are quite close to the value that we wanted. And that is how we design Miller capacitors, load capacitors, and calculate the higher cutoff frequencies of the amplifier using Miller. So yeah, see you in the next video for other analysis techniques. Thank you for watching.